Good morning, everyone. We're group 2, and today we'll be presenting our project, RUUV, or also known as RUUV. I'd like to briefly begin by going over what content we'll be covering in our presentation today. First, we'll go over why we selected this specific project and how we'll be addressing it. Secondly, we'll go over the 3 design elements we plan on implementing within our project. Then we'll also discuss what we hope to accomplish from our midpoint presentation to our final presentation. And lastly, we'll provide a brief update on the current status of our project.
Hi guys. Overexposure to UV rays is one of the leading causes of cancer worldwide, with skin cancer being one of the leading causes of that cancer. In fact, over 90% of skin cancers are caused by exposure to UV rays. Now, UV rays do more than just cancer. They cause wrinkles, redness, rashes. That's not pretty to look at. We do have sunscreen for that though, to prevent those symptoms, but sunscreen can be annoying to use and expensive to reapply, especially when you don't even know if you need it, depending on the intensity of the sun. What if there's a product that tells you how much UV you're being exposed to so that you can protect your skin in a better way? Well, now there is. Introducing.
So with RUUV, we aim to take into consideration that different skin tones provide different levels of protection against the sun based on melanin concentration. So sensors will be used to monitor the user's exposure to UV radiation and compare that to their melanin concentration. And it will be able to provide them with a custom reading of whether or not they are experiencing hazardous UV exposure at the moment. And if they are, the app will provide them with a notification.
So introducing the theory behind RUUV, I want to begin with ultraviolet radiation itself. So the UV spectrum is composed of 3 different wavelengths, UVA being the longest and UVC being the shortest. Now of those 3, UVC is entirely absorbed by the ozone layer, so that only leaves UVA and UVB actually coming into contact with our skin. And you can see the percentages that makes up on the screen there. And of those 2, we are primarily going to focus on UVB. That has the most health impact, and we'll get into that in the next slide. And the UV index that everyone sees when they open the weather app in the morning, that's simply the measure of the intensity times a constant of 40 meters squared per watts to make it readable for a table. And the UV dose is the intensity times the time, and that's really the metric that we're going to be focusing on because that actually determines whether or not the amount of UV you're exposed to is dangerous or not. And the governing principle behind all of our equations and colorimetry in general is governed by Beer-Lambert's law, which relates the intensity and the transmitted intensity to concentration of a sample and the length of the path that the light takes. So, as I mentioned before, UVB is a dangerous wavelength that we talk about, and that's because of the formation of cyclobutane pyrimidine dimers, or CPDs. And what these are is basically a disruption in the nucleotide base pairings, and what that leads to is mutations in the genome that impacts DNA replication. So that happens from UVB itself, that doesn't happen from UVA or anything, so you can see that's why we want to focus on that. And the literature shows that there is an estimation of 0.04 CPDs formed per UVB photon being absorbed by the DNA. So using that, let's derive the math a little bit. We see that we want to get the number of UV photons actually absorbed by the DNA, so we can multiply the UV dose of the transmitted wavelength to the cross-sectional area of DNA and divide that by the energy of the UV photon, also given by Planck's law. And also we see that the transmitted intensity is, again, another manipulation of Beer-Lambert's law, where the coefficient mu represents the absorption coefficient of melanin, and the coefficient d represents the depth of the skin, or how much the wavelength actually has to go through to reach the DNA. So putting all that together, we can turn this into a probability equation, and that's basically the principle we're going to use to determine whether or not the melanin in your skin is sufficient enough to block out the probability of a CPD being formed.
So these are the materials we'll be using for our project. This includes some basic materials such as just wiring and the breadboard for basic circuitry and connection. And we'll also be using an Arduino Nano 33 IoT to help read inputs and produce outputs. But the 2 biggest parts of our project involve our Adafruit, which is our UV sensor, and our spectral sensor, which can detect light wavelengths, which Evan will go into on the next slide.
The Adafruit UV sensor detects ambient light and UV radiation, providing precise UV index readings. Unlike most sensors that only estimate UV index, this sensor directly measures ultraviolet radiation, providing accurate exposure tracking. This sensor does it through 2 detection channels. one for visible light and one for ultraviolet radiation, which then feed into a microcontroller using an I2C interface, making integration into a wearable device easy. The reflectance sensor is a 6-channel visual spectral sensor that measures how light interacts with a surface by measuring the reflected light through 6 distinct wavelengths from 450 nanometers to 650 nanometers. The sensor shines a concentrated light source onto the skin and measures the reflected light using integrated nano-optic interference filters. By analyzing the difference between the emitted light and the reflected light, we're able to get properties like skin tone, melanin content, and light absorption.
So as mentioned before, we'll be using the Arduino Nano 33 IoT, which is fully programmable through Python. And from there, this microcontroller also has Bluetooth capabilities, so we aim to leverage these capabilities for the second part of our project, which will actually be a software app that users can use to get real-time updates on their current UV exposure. We hope that we can use the sensors in our microcontroller to get real-time changes based on their environment. And this way we can send notifications out when they're at high levels of exposure so that they can know to apply more sunscreen or go to a different environment. And we can also gather user data through this app just so that we can get a better sense of what their specific risks may be based on what their personal health aspects are. And we also want to make sure we can provide a friendly user interface so it's accessible for any user.
So what are our future directions? We want to create a compact design that's ergonomic and wearable. So we want to test multiple different CAD designs using multiple different filaments to see which one is the lightest, which one fits all of our parts, and which one looks the best. Anything for the user.
So continuing with our future directions, more on the compact side, for our future goal of it being wearable technology, because this will allow for the best user experience. Some considerations that we have in mind in order to achieve this goal would be a power source, as long as a way to charge the power source, and the comfort and durability of the device while being worn. And lastly, we want to consider a display screen so that the user can read the data directly from the device.
So our parts have been ordered and will be arriving sometime this week. We've also deeply been engaging with our mentor, Dr. Pierce, regarding the preliminary planning of our wiring and circuitry. And we're also excited to use a lot of the information we mentioned in our prior slides to further progress our project and create the most functional version of our project possible by the final presentation. Thank you everyone for your time.